Right, now that we've found a couple ways to determine if a series converges or diverges, we're going to find ways to compare those to other, maybe more complicated series. And this will allow us to find convergence and divergence of many more series by just relating them to something that we already know. So to do a quick recap of what we've seen so far, we have the nth term test, geometric series, telescoping series. We have the integral test, which we learned in the last lesson, saying that if if we take the integral of a series, if that integral converges, so does the corresponding series. If the integral diverges, so does the corresponding series. And through the integral test, we could show the general case, which we call the p series. If you have anything of the form, the sum of 1 over n to the power of p, if that value of p is greater than 1, the series converges. If that value of p is less than or equal to 1, the series diverges. So the big idea today is that if we know a certain series converges or diverges, we can make a statement about something that maybe looks a little similar, and we'll see how we do that. Okay, first thing we'll look at is called the direct comparison test. And you can see the conditions here for the direct comparison test. So we have two series. One is the series of a sub n, the other one b sub n. And if the terms a sub n are always less than or equal to b sub n, and if b sub n converges, we can conclude that the sum of a sub n must also converge. And this should make sense because a sub n is always below b sub n. So if those terms from b sub n are going to add up to some finite value, then the sum of a sub n must also add up to some value. Now again, if we have a sub n less than b sub n, and a sub n diverges, well, since b sub n is always above a sub n, it must diverge as well. So notice with the direct comparison test, we have to have the inequality the right direction to make a conclusion. So there are times where the direct comparison test just isn't going to work if our inequality doesn't go the right way. Okay, let's go ahead and visualize the direct comparison test. Now, we only apply the direct comparison test if the terms of the two series are greater than 0, so we're only dealing with positive terms here. So if we have this series in blue, and if that series converges, then the series in red is below, it must also converge. And if we have this series in red, which diverges, since the series in blue is above, it must also diverge. All right, so we want to prove that this series converges. So we're going to relate this to a series that is a little bit simpler. And the way you go about this is just thinking, okay, as n gets really big, what about this maybe isn't going to be as significant, and that plus 3 right there isn't really going to make much of a difference when n gets really large. So we'll compare this to 4 to the n over 5 to the n, and 4 to the n over 5 to the n plus 3 is always less than or equal to 4 to the n over 5 to the n, and we can rewrite that as 4/5 to the n. So we should realize that if we take the sum from n equals 0 to infinity of 4/5 to the n, that's a geometric series, r equals 4/5, which is less than 1, so that series converges. Therefore, the original series, the sum of 4 to the n over 5 to the n plus 3, must converge by direct comparison. Okay, the limit comparison test. So again, we're going to deal with a sub n and b sub n being positive terms. Well, we can take the limit as n goes to infinity of the terms of one series over the other. If that equals some value, we'll call it c, where c is greater than 0, less than infinity. So c is some number not equal to 0. Then those two series have the same behavior. They both converge or they both diverge. All right, so we want to take a look at this and determine, does this converge? Well, we're going to compare this to n over n squared, which simplifies down to 1 over n. And if we first tried to use direct comparison, we would have this inequality, n over n plus 1 squared is less than or equal to 1 over n. But we know that the series, the sum of 1 over n, is the harmonic series that diverges. So this inequality doesn't tell us anything. So a direct comparison test isn't going to work. So we need to rethink things, and now we'll go ahead and try limit comparison. So trying limit comparison instead, take the limit of one over the other, use some algebra to simplify that down, and we know that that plus 1 is going to be insignificant as we go towards infinity, This is the limit as n goes to infinity of n squared over n squared, and that's 1, which is a number between 0 and infinity. So both of these series have the same behavior. Since the sum of 1 over n diverges, being the harmonic series, the sum of n over n plus 1 squared also diverges by limit comparison. Take a look at this one right here. We have to think about what we could compare this to. Well, we know we could drop that minus 1, and you actually have some choices here. You could compare this to the series 3 over 2 to the n, or you could compare it to the series 1 over 2 to the n. It really doesn't make much of a difference. They'll both give you the same conclusion in the end. So I'm going to compare to 1 over 2 to the n, take the limit as n goes to infinity of the original over the one I'm comparing it to, use some algebra to rearrange things. I can bring that 3 to the outside, and this limit equals 3. That's a value greater than 0, less than infinity. Since 1 over 2 to the n converges, being a geometric series with common ratio less than 1, the series that we started with must also converge by limit comparison test.